So this is going to be the shortest section for you of video. I'm going to answer the questions, but I realized by their content that questions 16, 17, 18, 19 for me are from section 7.4, which ultimately we had removed those from our coverage. So we stopped at 7.3 and we didn't do 7.4. I'm interested to look at the rest of the practice final and see if it's going to cover 8.5. And I'll definitely make sure that the final exam does not have any of these questions on it. Since it's all for practice anyway, I'll go ahead and just let you deal with it. And people have already started this test, so I can't modify it now. So this question is dealing with the chi-square distribution. It says in statistics, the statistics of a sample size of 22, a sample standard deviation of 14.3 result in a 95% confidence interval of blah. So they've already worked out the confidence interval about the population standard deviation. And by the way, that alone will remind you that it's not from a section we covered, because that's right here where they're talking about a confidence interval, and this is about the variance. But all we do is we just take the square root of all these three pieces, and then we have a confidence interval about the standard deviation. So you know it's not something that we covered. Anyway, so the confidence interval can also be expressed as blah. That's true. If those are your lower and upper limits of your interval, you could express it in this interval notation. Then it says, given that 15.7 plus or minus 4.7 results in the values of this, essentially what they did is they took 20.4 and 11.0 and they averaged that, and they got 15.7. And then they took 20.4 minus 15.7, they got 4.7, and they put it in this other scientific notation. But so they say, since that is equal to those limits, to those values, can the confidence interval be expressed as 15.7 plus or minus 4.7 as well? Now if you watch my last video, you might tend to say yes. Sure, it's just another way we denote it, right? Let me go down here. I'm sorry, let me go up here. And we talked about how for the estimation of the population proportion, you can write it this way, you can write it this way, you can write it that way, right, with numbers involved. That is true because this is based off of a normal standard deviation, or it's based off of a normal distribution. So it's not, and it also would have worked for section, and that was section 7.2. It also would have worked for section 7.3, also again based off of a normal distribution. The problem is the chi-square distribution, which we would need for the problem that we're looking at, is not based off of a normal distribution. And let me see if I can show you an example of it. And when I say that, I mean it's not generally based off of it. So it depends on your degrees of freedom, which in other words depends on your sample size. But if the sample size is small, you're going to have a lot more skew to it. If the sample size is bigger, you're going to have less skew, especially if the sample size was, as large as the population size, right? Then you've got the full population, and at which case it's just basically a census. Our sample size is 22, so we expect quite a deal of skew. Anyway, let me come back down to this. No, this using 15.7 plus or minus 4.7 would imply that the sample standard deviation was 15.7, and it's not. We were given the sample standard deviation of 14.3. So in general, a confidence interval for the sigma or sigma squared does not have S at the center. Anyway, you want to learn more about this, you go to 7.4, and that was not required. You can also just peruse through the PowerPoints. So that would be the answer to that. Number 17, also from section 7.4, says use the given information to find the number of degrees of freedom. The critical value, this is the left critical value of the chi-square distribution, and the right critical value of the chi-square distribution, and the confidence interval altogether. to estimate the standard deviation. Is it reasonable to assume that the simple random sample has been selected from a population with a normal distribution? Sorry, it is reasonable to assume. Okay, so that just means that we can run the numbers, and so we are going to use this chart, which is also on our formula sheet, to get our critical values. And you know, I'll go back to the PowerPoint. We were just looking at this slide here to remind us that the degrees of freedom will be found similar to with the t-distribution that we were using earlier. It's going to be n-1. So since our sample size is 25, we will have a degrees of freedom of 24. The left critical value will be found by using our confidence level. And let me just show you their example. Our confidence level is 90%. Their confidence level was 95%. So they ended up splitting the difference for the two tails and making it 2.5% in each tail. We're going to go ahead and have a full 5% in each tail. So what we want to do is have 5% over here. Now read, let's scoot it down a little bit. Read the description here. To obtain the critical value, locate the degree of freedom at the top left column, and then locate 0.975. Now that's because if theirs is 95%, and then they want to have the additional 2.5%, that sum is 97.5. So what we're going to do is we're going to go to that table, and ours is going to be 5% plus 90, so we're going to look up 95%. Which is right here, even though it's super tiny, even for me, so it's got to look worse for you. And our degrees of freedoms are 24, which is right here. So that would be 13.848. That is tiny. Let me see if I can get us a bigger version. Okay, here we are. Alright, so 95, that's again the 90% confidence level plus the 5% on this tail. Coming down to 24, you get 13.848. A little too big, I'm sorry. Okay, so 13.848. Okay, and then for the right, this is going to be just 5%. So it's that complement of alpha over 2. So alpha is 10% because our confidence level is 90, and alpha over 2 is 5%, and so that's going to be right here. I'm going to scroll down to 24. I'm just going to put it down here at the bottom. And that should be right there, 36.415. The reason they may make this so small is because then you can see all the pieces. Scroll down there to 24, and you can see that 36.415. Okay, then the confidence interval. To do this, we need to take those two critical values we just found, and the sample size we have, and the standard deviation we have, and put them all here, and then we take the square root of each piece. So I'll do that quickly. Now, it might seem a little counterintuitive that we are putting the right critical value from the chi-square distribution first. Let me come over here. because, you know, the right side's the bigger one. So that might seem a little bit counterintuitive, but it should make sense that the lower limit would have a bigger divisor to make this entire number smaller, right? So anyway, go back here. The lower bound is going to be this if we were doing the confidence interval about the variance, but we're not. We're doing the standard deviation. So we take the square root of that. So that's going to be 2, let's see, they want 2 decimals, so 0.21. And by the way, this is fitting around already. You can see the sample standard deviation, which is your best point estimate. But remember, we're not assuming, as we learned from question 16, that this is going to be the center. That's not usually the case. If n was a really big number, it would be more likely to be the case. Or it would be, depends on how big it is, but it could be the case. But generally speaking, that's not the case. Okay, and then the other side, oh, what did I do? Oh, I used a negative symbol instead of the subtraction. In case that ever comes up to you as an error. Okay, so then the other side and square root. .34 hundredths. All right, so there should be a way to do this in StatCrunch. There is a way. We're trying to create a confidence interval about the variance with one sample with summary data, summary information. So the sample variance we had was 26 hundredths, the sample size was 25, the confidence level was 90. It will know to use the chi-square distribution. Hit compute, and it gets us these numbers, and then we would be taking the square root of each of those. Let's see if those agree. They don't agree. In fact, they're way off, because when I take the square root of 17 hundredths, I'm getting 41 hundredths, square root of 45 hundredths, and I'm getting 67 hundredths. And that they don't even seem reasonable to me, because if our sample standard deviation is 26 hundredths, there it is. I just realized when you're using this tool to do all the work for you, you're going to do variance stats, one sample with summary, and you're going to put in sample variance. I put in the sample standard deviation because, again, that's what we were trying to do. And so I just need to be careful. So here's 26 hundredths squared, 676. Okay, compute. And now I've got these numbers, which I'm pretty sure will agree. Let me just run them really fast. Alright, they are agreeing. We've got 21 hundredths and 34 hundredths. So make sure that you put in, if you're going to use StatCrunch to do all the work for you, put in the, let me go through the whole list again. You go stat, variance stats, one sample with summary, and fill in the sample variance and the sample size and the confidence level and all that stuff. So there's our interval. If you're going to be using the TI calculator for this work, you probably should just go ahead and use stat. It's probably under I guess they don't have one, not on the TI-83. I think it's on the TI-84. This one has a hypothesis test using the chi-square distribution, which you could work around and use for this, but it doesn't have an interval, so we'll have to stick with what we've got. either doing it by hand or using StatCrunch. Okay, again, another problem, and you don't have to watch any of these videos because this is section 7.4, which will not be on the final. But let's do this time. I'm going to do it quickly because I've already got StatCrunch here. Okay, stat variance, one sample with actual data. Take it from there. Use a confidence level of 80%. And I will store that in the table. Okay, so then here's my sample variance. Here's my lower limit and upper limit that bounds, creates the confidence interval to bound the population the population variance. But what they want is the standard deviation. So the reason why I stored it into the table is because now I can do something like this. I can do data, compute expression of the lower limit actually I want to first do, where's square root? Square root of the lower limit. Okay. And then data, compute expression, build, square root with the upper limit. So we're looking at how many decimals? 1 as needed, 3.7, 6.5. Does the confidence interval describe a standard deviation for all times during the week? Choose the correct answer below. And I would go with no, the confidence interval is an estimation of the standard deviation of the population of speeds at 3:30 on a weekday, not other times. Number 19 we're going to try and fit in. Which is going to reverse our calculations. Let me show you, similar to the other problem that we did. They didn't already do the algebra for us in the PowerPoints, so I will see if it's on our formula sheet. Okay, so here is the 30%, and the value of the standard deviation, the sample size, n should be at least 38. So we'll put in 38 here. And then it says a histogram of a sample of those arrival delays suggests that the distribution is skewed, not normal. So how does the skewed distribution affect the sample size? Well, the computed minimum sample size is not likely to be correct then, because it's not going to be predictable, because it's not normal. So let's go ahead and choose A. And then let's submit the test. And we see here we got number 16 correct then. And then number 17 was correct. And 18 correct. And let's see, 19, it shows partial. The minimum sample size was 38. And there was just a typo here. I clicked the wrong one. I meant to click A. So I made a mistake or something happened. But either way, in this case, I'd still get half credit, but I meant to choose A because if a histogram of the sample shows that the distribution is skewed, then it's not going to be predictable. So if it's not normal, it affects whether or not we can use this. So anyway, that would be a mistake that you could find after your test is done, but I wouldn't be able to give you any credit back for it. Now don't worry, because all these questions, 16, 17, 18, 19, are all from section 7.4, and they will not be on the test. Okay.